This is week 7 of thermodynamics course. So this is an overview and problems regarding what we saw in the previous lectures, weeks. So we'll have a mix of problems here. So starting with the first question is, a proposal is made to use a geothermal supply of hot water to operate a steam turbine as shown in figure. So a figure is shown and you're using a geothermal supply of hot water to run a turbine. So they are saying that the high pressure water, which is at 1.5 megapascal and 180 degrees Celsius, is throttled into a flash evaporator chamber. So it's throttled and so we have used. So in this case, we are using a geothermal hot supply of water to run a turbine to generate power. So initially, the water, which is at 1.5 megapascal and 180 degrees Celsius, is throttled and into a flash chamber, where it is separated into liquid and vapor, and the vapor is used to run the turbine. So the flash chamber is at 400 kilopascal. The liquid is discarded, and while saturated vapor feeds the turbine and exits at 10 kilopascal with a quality of 90%. So if the turbine should produce 1 megawatt, find the required mass flow rate of hot geothermal water in kilograms per hour. So how much amount of water is required? So at state 1. So that's what is asked. So we know the turbine is generating 1 megawatt of power, and your exit is at 10 kilopascal, and your vapor fraction is 0.9. So that is given, and your inlet is at 400 kilopascal. This is what is known. So what we'll do is we know at each points, so we can find out enthalpy, pressure and temperature. So we will go to steam table, we will find out the temperatures corresponding to temperature and pressure. We will find out the enthalpies. So at state 1, which is at 1.5 megapascal and 180 degrees Celsius, we will find out that your enthalpy is 763.5 kilojoule per kg, and then same enthalpy will be there at the flash chamber, because this is a throttling process. So if you apply your steady flow energy equation across your throttle, so you will see neglecting kinetic energy and potential energy, so you don't have any heat transfer or work transfer. So your enthalpy which is coming in will be equal to enthalpy which is going out. So your enthalpy will be constant. So H1 will be equal to your flash chamber enthalpy. So this flash chamber, which is at 400 kilopascal, will split into vapor and liquid. So we need to find out at what is the fraction in which your vapor is getting splitted. So corresponding to 400 kilopascal, we will find out the corresponding saturated vapor and saturated liquid enthalpies. So H1 will be equal to 763.5, which is the inlet, which will be equal to your enthalpy of liquid plus your vapor fraction into latent heat, which is saturated vapor enthalpy minus saturated liquid enthalpy. Your saturated liquid enthalpy is 604.74, and your latent heat, that is a Hg minus Hv, is 2133.8. So now substituting this in the equation, we'll find out that your vapor fraction in the flash chamber is 0.07439 or 0.075. So that is the fraction in which your vapor and liquid is getting splitted. So this gives your relation between mass of steam at state 2 by mass at state 1. So 1 kg, if 1 kg of water is given here after flashing, so you will have 0.07439 kgs of saturated vapor. So now corresponding to enthalpy 2, we know it is at 400 kilopascal and it is a saturated vapor. So for that, the corresponding enthalpy is 2738.6 kilojoule per kg. And enthalpy at state 3. So state 3, we know this is at 10 kilopascal and your vapor fraction is 0.9. So using that, for 10 kilopascal, saturated liquid enthalpy and saturated vapor enthalpy is found out from steam table, and we'll use relation to find out enthalpy at state 3, so which will come out to be 2345.4 kilojoule per kg. So now we know inlet enthalpy and exit enthalpy, and we also know the mass flow rate fraction. So substituting that, we know the total work generated, which is 1 megawatt. So converting, substituting that, and your enthalpy is in kilojoule. So we are substituting your work in kilowatts. So 1000 kilowatts, 1 megawatt is 1000 kilowatts. So 1000 divided by enthalpy difference, which will give me mass flow rate. So M2 is 2.543 kg per second. So that is my mass flow rate. So substituting in the mass flow relation, we will find out that your mass of water which is required at state 1 from the geothermal well where you are getting the supply of hot water, from there you will require 34.19 kgs per second, or 123075 kg per hour multiplied by 3600. The problem is asked to find out in hour. So 34.19 into 3600 get 123075 kg per hour. So that was a simple problem. We'll see the next one. We have a 200 liter tank, initially contains water at 100 kilopascal and a quality of 1%. So the tank capacity is 200 liters and your pressure inside the tank is 100 kilopascal, which is containing water, and the quality is 1%. So that means 1% vapor and rest 99% is liquid. Heat is transferred to the water, thereby raising its pressure and temperature. At a pressure of 2 megapascal, the safety valve opens and a saturated vapor of 2 megapascal flows out. So initially this tank, which is at 100 kilopascal, is heated such that your pressure increases to 2 megapascal, after which the safety valve will open and saturated vapor will exit. The process continues maintaining 2 megapascal inside until the quality in the tank is 90%. Then stops. Determine the total mass of water that flowed out and the total heat transfer. So you see there are two types of processes which is happening. So initially when the tank was filled with water plus water vapor, it's 1%, and when you are heating it, this is a constant volume process, because your volume is constant, you are adding in heat, so your temperature and your pressure inside the vessel will increase. Then when it reached 2 megapascal, your safety valve opened, and then you are again heating it. Now the pressure is maintained constant at 2 megapascal. So we'll see how to solve this. So now control volume is across your tank. So if you see, there is no work transfer, but there is heat transfer. So assuming initially state 1, which is the initial state where the valve was closed, then state 2 when the valve was open, and state 3 when final state when your vapor fraction is 90% and your pressure is 2 megapascal. So those are initial state points. So when you apply a continuity equation, so initially the tank contains some mass m1. At the end state, your mass which is there in the container is m3. So in between state 1 and 3, or state 1 and 2, there is no mass transfer because the valve was closed, and 2 and 3 there is valve opened and some mass left. So between this 1 and 3, there is some amount of mass which is exiting. So we denote it as me. So m3 minus m1 is equals to minus me. So this is what we get applying a mass balance. Next we will apply the energy balance. So initially from state 1 to state 3, so initially there is no a fluid coming in, but there is enthalpy which is the fluid which is going out. So enthalpy of that and will be equal to the heat transfer which is happening and then the change in internal energy. So applying your steady flow energy equation, so your change in internal energy with respect to time du by dt, you can write it as m3u3 minus m1u1. So this is your change in internal energy. This will be equal to your mass of enthalpy of stream which is exiting, so minus MEHE, plus your heat which is getting transferred during process 1 to 3. So these are the two equations which we get. So now starting at state 1, we know that it is a 100 kilopascal and the quality is 1%, and this is a 200 liter tank. So for 100 kilopascal, the corresponding liquid and vapor specific volumes we can get it from steam table. So using that we can find out the total specific volume of the fluid in the tank. So V1 equals Vf plus X into Vfg. So X at state 1 is 1%, so 0.01. So substituting, we will get that the specific volume at state 1 is 0.01797 meter cube per kg. So then we will also find out the internal energy. So internal energy is U1 equals same relation using your liquid internal energy and vapor liquid internal energy, saturated liquid and vapor. So substituting, we know X value. So on substituting, so we will find out that the internal energy at state 1 is 438.22 kilojoule per kg. From this we know the total volume of the system, so we can find out the mass of the system. So M1 is nothing but your volume divided by specific volume. So volume is 200 liters. So 1 liter is 10 power minus 3 meter cube. So into 200 into 10 power minus 3 will give me 0.2 meter cube. So we know specific volume. So volume by specific volume will give me the mass at state 1, which is 11.13 kg. So this is the amount of water which was there at state 1. So now at state 3, similarly, which is at 2 megapascal and 90% quality, so we can find out the corresponding specific volume at 90% vapor. So we'll find out V3 as 0.8978 meter cube per kg, and then internal energy correspondingly is 2430.88 kilojoule per kg. So now mass at state 3 is, again you have 200 liters with specific volume was 0.8978. So mass at state 3 is 2.23 kgs. So using this, and we also know the stream which is going out, which is at 2 megapascal, which is saturated vapor. So correspondingly enthalpy of that is 2799.51 kilojoule per kg. So now we know all mass and internal energy and enthalpy. So now substituting in the equation, we can find out the mass which is exiting, is m1 minus m3, will be equal to 8.9 kg. So this is the amount of water steam which is going out of the cylinder. Next, applying the energy balance equation, we can find out the heat transfer which is supplied to the tank in the process, and it will come out to be 25.46 megajoules. So this is the amount of heat which is supplied to go from state 1, which is at 100 kilopascal and 1%, to state 2, which is at 2 megapascal and 90%. So moving on, we have a steam engine based on a turbine is shown in figure. So it contains a boiler whose volume is 100 liter, and initially contains saturated liquid with a very small amount of vapor at 100 kilopascal. So heat is now added by the burner, and the pressure regulator does not open before the boiler pressure reaches 100 kilopascal, which it keeps constant. So the saturated vapor enters the turbine at 700 kilopascal and is discharged to the atmosphere as saturated vapor at 100 kilopascal. The burner is turned off when no more liquid is present in the boiler. Find the total turbine work and the total heat transfer to the boiler of this process. So this is just like a combination of the first two processes we saw. So we'll see how to solve this. So initially there are we'll consider two separate control volumes, one for the boiler and other for the turbine. So boiler, there is no work transfer, so there is one heat transfer, and there is a mass which is going out. In turbine there is no heat transfer, but there will be fluid which is coming in and going out, and there is a work transfer. So and it is operating in steady state. So for first, when you apply for boiler tank, so similar equation, mass balance m2 minus m1. So m2 is state 2 minus m1 state 1 is equal to mass of steam which is going out. So then applying energy equation, it will be equal to your similar equation, change in internal energy equal to heat transfer minus your enthalpy going out. So from steam table we can find out for 100 kilopascal at state 1 your specific volume. So this initially there is no negligible vapor, so you can assume that it's totally liquid. So specific volume there is 0.001043, and we know volume was 100 liters, so 0.1 meter cube divided by specific volume will give me 95.877 kg, and the internal energy is corresponding to that saturated liquid internal energy is 417.36 kilojoule per kg. Now at state 2, which is at 700 kilopascal and fully vapor. So for fully vapor, we will take saturated vapor specific volume at 700 kilopascal, which will be 0.2729, and your internal energy at that point is 2572.5 kilojoule per kg. Now mass at that is, your cylinder boiler volume is 100 liters, so 0.1 divided by specific volume will give me 0.366 kg. Now the exit state is of the boiler is 700 kilopascal, so correspondingly you will take saturated vapor enthalpy, which is 2763.5 kilojoule per kg, and your turbine exit is this exit state of boiler is your turbine inlet is 700 kilopascal, and then turbine exit is 100 kilopascal. So corresponding to that, your enthalpy is 2675.5 kilojoule per kg. So now the mass at state 1 and state 2 in the boiler. From this we can find out how much mass is going out of the boiler. It will come out to be 95.511 kg. So we know mass, so we can find out how much heat which we have supplied using the energy balance equation. So rearranging, we get the change in internal energy plus the enthalpy which is going out. It will come out to be 224.9 megajoules. So this is the amount of heat which we are supplying, and the turbine work is your mass which is going out of the turbine boiler, which is going into the turbine. So m dot E into the enthalpy difference, H in minus H out. That is it. So substituting that, you will find out your work generated in the turbine is 8405 kilojoule or 8.405 megajoules. That's the amount of work which is generated in the turbine. So moving on to the next problem. We have a mass loaded piston cylinder which is shown in figure, containing air which is at 300 kilopascal and 17 degrees Celsius with a volume of 0.25 meter cube, while at the stop volume is 1 meter cube. So initially you are in the piston arrangement cylinder which is shown in the figure. Your pressure is 300 kilopascal and your temperature is 17 degrees Celsius with a volume of 0.25 meter cube. Then when it reaches the stop, your volume is 1 meter cube. This is connected to an air line where the air supply is at 500 kilopascal and 600 Kelvin. This is connected to the piston using a valve. Now this valve is open until a final inside pressure is of 400 kilopascal. So at this point your temperature is 350 Kelvin. So you need to find out the mass of air which is entering, the work done, and the heat transfer which is taking place. So we'll see how to solve this. So now we'll have to apply control volume across the cylinder, piston cylinder arrangement. So and you have to apply a mass balance. So initially your mass was m1 and at the final state your mass is m2. So the change in mass is min. So m2 minus m1 equals to min. Similarly, you apply an energy balance equation. So m2 u2, this is change in internal energy, equal to the enthalpy which is coming in plus heat added minus work done. So m2 u2 minus m1 u1 equals m in h line enthalpy in the line, which is the enthalpy entering the cylinder, plus QCV is the heat transferred to the control volume minus work done in the process 1 to 2. So initially two types of process happens. So initially when the piston is moving till it reaches the stop, your pressure is constant, and then when it reaches the stop, your volume becomes constant and your pressure starts increasing. So at state 1, you know P1, T1. So you can find out mass 1. So P1V into divided by RT1, your ideal gas relation. So P is 300 kilopascal into volume 0.25 meter cube, which is given, divide by air. So air gas constant is 287 into 290.2, which is the temperature. So substituting this, we will get mass as 0.9 kg. And again at state 2, you know pressure is 400 kilopascal, your temperature is 350 Kelvin. So substituting that, and your volume is 1 meter cube. So substituting that, you will find out mass at state 2 is 3.982 kgs. So the mass which has entered the cylinder is the difference between these two masses, and it will be 3.082 kg. So when you consider initially, when the piston is moving and it does not reach the stop, till that point your pressure will be constant. So for that your work done is P1 into change in volume. So P1 is your initial pressure 300 kilopascal into volume is state 2 is 1 meter cube and at state 1 is 0.25. So the difference in that it will give me 225 kilojoule. So this is the amount of work which is done initially when the piston moves till the stop. Then it's a constant volume process, so your work done will be 0 from after that. So from there your internal energy starts increasing. So when you do an energy balance, so you can find out heat transfer. So you know the work transfer between the states, you know the enthalpy which is coming in, your mass which is coming in, you know the internal energies. So substituting that, so M2 into U2, U2 is written as CV into T. CV of air is 0.717 kilojoule per kg Kelvin. So and at state 2 your temperature is known as 350 Kelvin, and similarly at state 1 you can find out internal energy, and the work done is 225 minus your mass which has come in is 3.082 into Cp. Cp is 1.004 and your air temperature is 600 Kelvin. So substituting that, you will find out your Q is minus 819.2 kilojoule. So this is the amount of heat which is rejected during the process. So moving on, the next problem is we have a 2 meter cube storage tank which contains 95% liquid and 5% vapor by volume of liquefied natural gas at 160 Kelvin as shown in figure. It may be assumed that LNG has the same properties as pure methane. So this cylinder contains LNG which is 95% liquid and 5% vapor at 160 Kelvin, and heat is transferred to the tank and saturated vapor at 160 Kelvin flows into steady flow heater which leaves at 300 Kelvin. The process continues until all the liquid in the storage tank is gone. Calculate the total amount of heat transferred to the tank and the total amount of heat transferred to the heater. So initially you have a tank containing LNG with 95% liquid and 5% vapor. You are supplying heat to make the liquid evaporate, and the vapor is taken out at 160 Kelvin and it is heated separately in a heater to 300 Kelvin. So what is the total amount of heat which you are supplying in the tank and in the heater? That's what is been asked. So similarly, we can find out how much amount of heat, mass which is going out of the cylinder using the same equations which we used in the previous problems. So apply across a control volume across the tank. Your mass at state 1 is M1 and state 2 is M2, and mass which is exiting is Me. So energy equation again across tank, your internal energy change plus equals your heat transfer and minus your enthalpy which is going out. Then at 160 Kelvin, from the property table for methane, we can find out the specific volume at 160 Kelvin. Saturated vapor is 0.00297, which is so volume occupied is 95%. So your volume is 0.95 into 2. Your storage tank capacity is 2 meter cube. So 2 into 0.95 is occupied by liquid divided by liquid specific volume. It will give me the mass of liquid which is present at state 1, which is 639.73 kg. Similarly for gas is gas volume divided by gas specific volume. Gas volume is 5%, so 0.05 into 2 divided by specific volume is 0.03935. Will come out to be 2.541 kg. So mass 1 is summation of these two, so will come out to be 642.271 kg. Similarly at state 2 we have total all saturated vapor. So saturated vapor enthalpy is known, specific volume is known. So and your volume will be 2 meter cube because the whole cylinder is full of saturated vapor, methane or LNG. So 2 by your specific volume will give me 50.826 kg. So from this we can find out the mass which is coming out of the cylinder. And similarly at state 1 we can find out the internal energy as your mass of liquid into internal energy, mass of liquid into internal energy of saturated liquid plus mass of saturated vapor into internal energy of saturated vapor, which will come out to be minus 67507 kilojoule. So and mass which is coming out of the cylinder is M1 minus M2, which is 591.445 kg. So the heat transfer is again, you apply energy balance, you substitute there. We know at state 1 you can find similarly mass is at state 2 is known, enthalpy which is coming out is known. So substituting that we will find out the heat transfer is 237931 kilojoule. So this is the amount of heat which is transferred to the cylinder. And then when you across heater, so we know inlet is your saturated vapor, which is at 160 Kelvin. So your pressure is 15393 kilopascal. Corresponding saturated pressure is 1593 kilopascal. Using this and exit temperature of 300 Kelvin, we can find out enthalpy at state exit of the heater, which is 612.9. So substituting this in the energy balance across the heater will be mass of LNG which is coming out of the tank into the enthalpy difference. So mass which is coming out is 591.445, which we calculated from the previous part, into your enthalpy difference, which will come out to be 202629 kilojoule. So this is the amount of heat which are supplying in the heater. So the next question is a somewhat simplified flow diagram for a nuclear power plant is given in figure. Mass flow rates and the various states in the cycle are shown in the accompanying table. So a simplified flow diagram of a nuclear power plant is given and accompanying table is given. The cycle includes a number of heaters in which heat is transferred from steam taken out of the turbine and some intermediate pressures to liquid water pump from the condenser on its way to the steam drum. So the heat exchanger in the reactor supplies 157 megawatt, and it may be assumed that there is no heat transfer in the turbines. So assume the moisture separator has no heat transfer between the two turbine sections. Determine the enthalpy and quality. Determine the power output of the low pressure turbine. Determine the power output of the high pressure turbine. Find the ratio of the total power output of the two turbines to the total power delivered by the reactor. So that is the efficiency of the reactor. So this is what the reactor diagram is. So you have reactor here where you are supplying heat of 157 megawatts, and then that is going into heating the steam and the steam drum, and from where your steam is getting generated, and then that steam you are supplying to the high pressure turbine. So the high pressure turbine exit, you are going separating into a moisture separator. So after expansion, you will have two phase. So you are separating liquid and vapor, and the vapor again you are supplying it to a low pressure turbine, the exit of which is going to a condenser, and then it's coming to a low pressure heater, pump to a low pressure heater, where you are mixing with the liquid which is separated from the moisture separator, and then if you see this pumped sent again to an intermediate pressure heater, where it's mixes with the liquid which is coming from the high pressure turbine, and similarly you are sending it back to the steam drum. And for each of the states, the corresponding mass and pressure and temperature is enthalpy is given in the table in the left. So now, so if we just consider the turbine and the moisture separator. So if you see your steam which is coming at state 2, and then you are taking bleeding it off at 17 and 12, and there is a exit at state 3, and there you are separating moisture, and at state 4 it's entering your low pressure turbine, and where you are bleeding it again at 8 and 5, exit is at 5. So initially, the first problem, we need to determine the enthalpy and quality at state 4, and we assume there is no heat transfer here. So we will do a mass balance initially, and so my mass 3 which is coming in will be equal to mass at state 4 and state 9. So from there we can find out the mass flow rate at state 4, which is M3 minus M9. So from the table, M3 is 62.874 kg per second, and the M9 is 4.662 kg per second. So substituting that, at state 4 the mass flow rate is 58.212 kg per second. So that is the mass which is entering the low pressure turbine. Now we apply an energy balance across the moisture separator. So if we apply an energy balance, so again enthalpy, there is no heat transfer, there is no work transfer, so it's just the enthalpy balance. So M3 H3 which is coming in is equals to the exit streams M9 H9 and M4 H4. So from energy balance we can find out enthalpy at state 4. So correspondingly enthalpy at state 3 is, you know, mass flow rate, you know, enthalpy is 2517. At state 9 mass is 4.662 and enthalpy is 558. So substituting that, and mass at state 4 we have already calculated. So substituting that, we will get enthalpy is 2673.9 kg per kilojoule per kg. So this is known. At state 4, you know pressure which is at 310 kilopascal, and you know the enthalpy. So corresponding to pressure of 310, you from the steam table you can find out the liquid and vapor enthalpy. So substituting that, we can find out the vapor fraction. So that will come out to be 0.9755. So that is the vapor fraction at state 4. So we have found out enthalpy and dryness fraction at state 4. Next is to find out low pressure turbine power output. So we'll do again an energy balance, mass balance across low pressure turbine, because we have two exit streams in the turbine. So initially we know inlet M4 and exit is M4 equals M5 plus M8, and energy balance again M dot 4 H4 will be equal to M dot 5 H5 plus M dot 8 H8 plus the work done. So from here we know 4, we have already calculated 4. The other unknown is 5 and 8, M dot 5 and 8. So we know mass at state 8, which is 2.772. Using that and mass balance equation, we can find out mass at state 5, which will come out to be 55.44 kg per second. and substituting the enthalpies from the table, substituting here, we will find out the work done is m dot 4 h4 minus m dot 5 h5 minus m8 h8. So substituting mass and corresponding enthalpies. So h5 and h8 enthalpies is given. h5 is 2279, h8 is 2459. So substituting that, you get the work produced in the low pressure turbine is 22.489 megawatts. Similarly, high pressure turbine history, there is 2 which is coming in, 17, 12 and 3 which is going out. So 2 which is coming in, mass flow rate is given 17, 12 and 3. So 3 mass flow rate is known, 17 mass flow rate is known and 12 mass flow rate. So all mass flow rate is known, so no need to apply a mass balance equation. You can directly apply an energy balance equation across the high pressure steam turbine. So m dot 2 h2 will be equal to m dot 17 h17 m12 h12 plus m3 h3 minus work plus work generated in high pressure turbine. So rearranging will get m2 h2 minus all the exit stream enthalpies. So substituting corresponding mass and enthalpy values from the table, we will get work as 18.394 megawatts. So this is the work which is generated in high pressure turbine. Then the last which is asked is the ratio of total work generated divided by the heat supplied. So heat supplied is 157 megawatts. So and your work generated in the low pressure turbine and high pressure turbine is 22 megawatts and 18.3 megawatts. So substituting that, you will get the efficiency is 0.26 to 26%. So the next problem is, the following data are for a simple steam power plant as shown in figure. So this is the figure, and the corresponding state. So there are 7 states. So and corresponding pressure and temperature is given and enthalpy is given. So question is half not visible. I think I have to change this. So anyway, we need to find out the turbine work here. So okay, here in the turbine, they have given your inlet turbine. You need to apply a steady flow energy equation. So you need to find out the velocities. So for that, the area of the inlet tube to the turbine is given as 0.2 meter. So area is pi by 4 by 0.2 raised to square. So it will give you the area and your specific volume at inlet to the turbine, which is state 5. So corresponding to temperature of 490 and pressure of 5.5. So your specific volume will be 0.06163 meter cube per kg, and your mass flow rate is given as 25 kg per second. So substituting that, you can find out the velocity at inlet to the turbine, which will come out to be 49 meters per second. So at enthalpy at state 6 is the exit. So exit is even similarly from the given state values, we find out enthalpy and you do an energy balance. so which is steady flow energy equation, which is inlet stream enthalpy minus exit stream enthalpy, and kinetic energy, inlet kinetic energy minus exit kinetic energy. So this is all in specific values, so divided by mass. So correspondingly we substitute the inlet and exit enthalpies and velocities. So will come out to be work generated is 24.8 megawatts. So I'll update this while uploading. I'll just add the question here. It's not visible. The next question is for the same steam power plant as shown in figure of the previous problem, assume the cooling water comes from a lake at 15 degrees Celsius and is returned to 25 degrees Celsius. So to the condenser, they are given inlet and exit. So determine the rate of heat transfer in the condenser and the mass flow rate of cooling water from the lake. So similarly, in the condenser, you apply the steady flow energy equation. So you are estimating the velocity at inlet and exit. So inlet to the condenser is at state 7. So exit of the condenser is at state 7, and the inlet is known 6 from the turbine. So H6 is known from the turbine previous problem, and 7 again from the problem the diameter is given. So using that you find out the velocity at state 7, and similarly you substitute in the steady flow energy equation across the condenser. So you have no work transfer in the condenser, so your W is 0, and this is a steady flow energy steady equation. So there is no change in energy term. D by dt is 0. So this will be nothing but your inlet enthalpy plus kinetic energy plus potential energy equals Q plus exit kinetic energy potential energy. So you rearrange, you will get Q as enthalpy coming in H7 minus enthalpy which is going out. Sorry, enthalpy which is going out H7 minus enthalpy which is coming in H6 plus half velocity going out square kinetic energy minus velocity square at inlet. This will come out to be minus 2245.2 kilojoule per kg. So Q condenser is nothing but mass flow rate into the specific Q. It will come out to be minus 56 megawatts. So this is the amount of heat which is taken from the condenser. So this will be equal to mass of fluid from the sea water which you are supplying, which is coming out 15 and 25. So 56130 divided by your enthalpy of water corresponding to 15 and 25. So substituting that, we can find out the mass of sea water which is required. This is 1339.6 kg per second. So the next question is mass m of helium is contained in a cylinder closed by a piston. The helium passes from an initial state 1 to a final state 2 according to the paths described below. The path 1 2 is isothermal expansion of volume V1 to volume V2 by very slow displacement of the piston. So slow displacement isothermal means you are going in reversible process. So and it's an isothermal expansion. Then path 1 1-2, which is an adiabatic expansion of volume V1 to volume V1 dash, which is equal to V2. So second is an adiabatic expansion. So from volume V1 to same volume V2 by very slow displacement of the piston, followed by an isochoric heating up to temperature T2 equals T1. So that's the two processes, and this is the data which is given. So V1 T1 and V2 T2, and then molar mass, then specific heat and mass. So question is to represent the process in a PV diagram and a TS diagram. Then calculate the pressure and temperature relative to state 1, 1 dash and 2. Calculate the change of entropy, the mechanical energy and heat energy for the two paths considered. So this is how the process will look. So state 1 to 2 is an, if you see in the TS diagram, so state 1 to was an isothermal process. So this is one way. The second one was 1 dash 2. So in that, first you are doing an adiabatic expansion, which is also slow, so reversible adiabatic. So 1 to 1 dash, so it's a constant interval process. Then 1 dash to 2, again it's an isochoric process, so your volume will be same. So that's what is shown. And similarly, if you see in a PV diagram, your temperature is shown. So 1 to 2 is an isothermal process. You have T1 equals T2, so it's across an isotherm. And then other is your against constant entropy line. So 1 to 1 dash and then constant volume, so 1 dash to 2. So this is how the process is represented in the PV and TS diagram. So the second one is to calculate the pressure and temperature related to all the points. So for helium, you first find out the gas constant, nothing by 8.314 divided by your molecular weight. So it will come out to be 2.0769 kilojoule per kg Kelvin. Then molecular weight is given 4, so you can use that. The isochoric specific heat is given, so using that you can find out constant volume specific heat. So it will be 3.1162 kilojoule per kg Kelvin, and then gamma is 1.67, which is Cp by Cv. So now initially at state 1, we know volume, we know temperature, which is given. So volume is 0.1 meter cube and temperature is 400 degrees Celsius. So you apply an ideal gas equation, so mRT1 by V1. So mass is given as 1 kg and R we have calculated 2.0769 and temperature is 300 degrees Celsius, 400 degrees Celsius. So 400 plus 273 divided by volume, so which will come out to be 139.81 bar. So this is at state 1. Now from 1 to 1 dash, it was an adiabatic process, so you can it is PV raised to power gamma equals constant. So okay, you will get P1 dash equals P1 into V1 by V2 raised to power gamma. So but in the problem it is given that V1 dash is equals to V2, and the data is given that V2 is 3 times of V1, so V2 will be 0.3. So we know this ratio is 1 by 0.3, sorry 1 by 3, and we know P1 139.81, so we can find out pressure at state 1 dash, which will be come out to be 22.41 bar. Now next is 1 to 2 was an isothermal process. So we know temperature at 1 and temperature at 2 is same, so T1 is equals to T2. Then pressure at state 2, so we know pressure at 1, pressure at 1 dash. So second is you either using constant volume process, or you can use one and state 1 dash and 2 assuming constant volume process, or 1 to 2 was an isothermal process. So we are considering an isothermal process way. So from there we will see P2 is V1 by V2 into P1. So V1 by V2 is 1 by 3, so pressure is known, so P2 will be 46.60 bar. So now initial and final temperature is known, so which is 673.15, which is 400 plus 273.15, and 1 dash to 2 is an isochoric process where volume is constant. So using that we can find out temperature state 1 dash, because we know temperature at 2, so we know at pressure at 1 dash, we know volume at 1 dash, which is equal to 2. So substituting all, again by using ideal gas equation, we can find out temperature at 1 dash as 323.67 Kelvin. which is nothing but 50.52 degrees Celsius. So now we have find out all pressures and temperature at all points. Next is we need to find out the change in entropy, the mechanical work done and heat transfer. So first is to find out the entropy change. Uh, so 1 to 2, if you say consider just process 1 to 2, there is an isothermal process. So when you expand, it can be expanded as MR ln P2 by P1 plus we'll have Cp ln T2 by T1. This is the ln isothermal process that will become 0. So we substitute the pressure values, we know mass, we know R. So substituting that, we will find out the change in entropy is 2.282 kilojoule per Kelvin. And you can straight away find Q as T into delta S. So this is an isothermal process. So Q equals Q by T is delta S. So T is constant. So we know temperature at 1 and we know delta S. So the heat transferred is 1535.93 kilojoule. The next is the change in internal energy. So internal energy is 0. So whatever heat transfer will be equal to work transfer. So that's what happens in isothermal process. So 1535.93 kilojoule is equals to the work transfer also. When you apply first law. So the next is to the process 1 dash, which is an adiabatic process. So it's an reversible adiabatic. So your entropy is 0, change is 0. So delta is 0. So Q is also will be 0. So from first law, your work done, work is represented as A here instead of W. So work done is equals to your change in internal energy across state 1 and 1 dash. So instead change in internal energy can be found out using MCV delta T. So MCV T1 dash minus T1, which will give me 1088.48 kilojoule. CV we have already found out as 3.1162, and we have also found out temperature. So substituting that, we can find out the work generated. Similarly, for process 1 dash 2, which is an isochoric process, your work done will be 0. So work done is P delta V. So your work done will be 0, and your change in entropy is MCV ln T2 by T1 minus your CV ln V2 by V1. You can assume that it becomes 0 because your volume is constant. So your entropy is MCV ln T2 by T1. So substituting the temperatures and CV value, we can find out the delta S is 2.282 kilojoule per Kelvin. So if you see the previously also during 1 to 2, you got the same entropy change. That's what happens in the entropy. See, if you see in the TDS, 1 to 2 is one way of going to from state 1 to state 2. The other way of going was 1 dash and 2. So if you see, ultimately your entropy, say being a state property, your change in entropy value will be same. So that's what is happening here. So you are getting 2.282 kilojoule per Kelvin. So when you apply a first law,
Good evening, sir.
good evening. Do you have any
Sorry,
question?
sir. Actually, the class used to conduct at 7 p.m. That's why I thought the class is at 7. Sorry for the late. I
Okay,
will
okay.
check all these classes from the video also. Okay, sir.
No issue, no issue.
Okay, sir. Thank you, sir.
So we have found out your delta is entropy change, and this being an isochoric process, your work done will be 0. So heat transfer is nothing but your change in internal energy from first law. So internal energy you can find out using MCV delta T. So we know the temperatures at both the states point. So substituting that, we can find out Q is 1088.48 kilojoule. So from 1 to 2, so So we just added up and we have shown what is the internal energy and the work done and the heat transfer. These are both the process. Here your heat transfer and work transfer is also same because this is a reversible process. So ultimately you are spending the same amount of work, but this may not be true for an irreversible process. The next question is, we have a refrigerant. You have any question on the previous problem? Okay. So next question is, refrigerant R134A flows at steady state through horizontal tube having an inside diameter of 0.05 meter. The refrigerant enters the tube with a quality of 0.1, temperature of 36 degrees Celsius and velocity of 10 meters per second. So we have a constant horizontal tube, a constant cross section. A diameter is 0.05 meter is given. 134A refrigerant is flowing inside, and your inlet quality is 0.1. And temperature is given as 36 degrees Celsius and 10 meters per second. And your exit pressure is 9 bar. So we need to find out the mass of refrigerant which is flowing in, the velocity of refrigerant at exit, and the rate of heat transfer, and into what direction the heat transfer is. Is it absorbing heat or is it rejecting heat? So that's what is asked. So if you see this tube with a cross section of 0.05 meter diameter. So inlet condition is shown 0.1 vapor fraction, 36 degrees Celsius and 10 meters per second, and exit 9 bar. So your mass flow rate is nothing but rho AV. Rho is written as specific volume 1 by specific volume. So into area into velocity at state 1. So you know diameter, you know 1, and you can find out specific volume at state 1. The specific volume at state 1 is nothing but at 36 degrees Celsius, corresponding saturated vapor and saturated gas, vapor and liquid specific volumes we take from the refrigerant chart for R134A. At 26 degrees Celsius, your liquid specific volume is 0.000859 and your gas is 0.0223 meter cube per kg. You substituting that, and you know vapor fraction is 0.1. So substituting that, we will get the specific volume at state 1 is 0.003 meter cube per kg. So we know specific volume, we know velocity, we know diameter. So substituting all values, we can find out the mass at state 1, which will come out to be 6.54 kg per second. So this is the mass at state 1. So next is to find out velocity at refrigerant at exit. So for that we will apply a continuity equation or a mass balance. So mass which is coming in will be equal to the mass which is going out, because in the horizontal tube this is a steady flow, steady state process. So there is no accumulation of mass inside. So mass which is coming in will go out. So m dot 1 equals m dot 2. So same rho AV, so or A2 V2 by specific volume at state 2 equals A1 V1 by specific volume at state 1. Because this is a constant cross section tube, your areas will be same. So A2 equals A1, so you can cancel out. So you know velocity at 1, so you know specific volume at state 1, so you can find out specific volume at state 2. Specific volume at state 2, they are saying that the tube exits saturated liquid at 9 bar. So corresponding from table, corresponding to 9 bar and saturated liquid specific volume will be 0.008576 meter cube per kg. So substituting that, we can find out velocity at state 2, which is nothing but 10 into your ratio of velocity specific volumes. Then it will come out to be 2.86 meter per second. And then we will apply an energy balance. The next is to find out the heat transfer which is happening, and this is being So there will be no work transfer. So work transfer will be 0. So you are applying a steady flow energy equation. So you will get QCV minus WCV plus m dot h1 or inlet minus exit. So m dot h1 minus h2, which is the enthalpy difference between inlet and exit, plus half v1 square minus v2 square, which is the specific kinetic energy between inlet and exit, plus m dot into g z1 minus z2, which is the potential energy difference between inlet and exit. So this potential energy, we assume that both are at the same height, so your potential energy difference will be 0. You know velocities at state 1 and state 2, which we have calculated, which is 10 and 2.86. We know enthalpy at 1 and 2. So 2 is your saturated liquid corresponding to 9 bar. From table it will come out to be 99.56 kilojoule per kg. And at enthalpy at state 1 is, again we know vapor fraction. We will find out liquid and vapor, saturated liquid and saturated vapor enthalpies for 36 degrees Celsius, and we will find out H1 as again F plus X into Hg minus Hf. So substituting the enthalpy values, we will get H1 as 116.87 kilojoule per kg. So if you see in the energy balance equation, the only unknown is the heat transfer, so the rest of we know. So we will substitute the enthalpy and velocity, and also mass is known, we have calculated, which is 6.54 kg per second. So substituting that, we will find out that the heat transfer which is happening is minus 113.5 kilowatt. So this suggests that that heat is getting rejected. So this negative says that heat is getting rejected, and you are losing 113.5 kilowatts. So initially, if you see this 0.1, it's converting into liquid. So ultimately, in that point also, if you see, you are condensing. So you have to reject heat in that case. So that's what we observe here, which is negative minus 113.5. The next question is a nitrogen gas which is contained in a rigid 1 meter cube tank, which is initially at 10 bar and 300 Kelvin. So this is a nitrogen tank which is volume is 1 meter cube and at 10 bar and 300 Kelvin. So heat transfer to the content of the tank occurs until the temperature has increased to 400 Kelvin. So initially it was 300 Kelvin, now we are heating it till the point it reaches 400 Kelvin. During this process, a pressure relief valve allows nitrogen to escape, maintaining constant pressure in the tank. Neglecting kinetic and potential energy effects and using the ideal gas model with constant specific heat evaluated at 350 Kelvin, determine the mass of nitrogen that escapes in kg and amount of energy transferred by heat. So this is similar to one of the problems which we saw previously. So the same process we'll see. So we will apply an mass balance across the tank. So you'll see the change in mass which is occurring is equal to the mass which is going out. So change in mass is nothing but your mass at state 1 minus state 2. So m1 minus m2 will be equal to the mass which is going out. So we can find this using can find mass at state 1 and state 2 using an ideal gas energy equation. So ideal gas equation of state. So PV equal to MRT. So at state 1, so PV by R into 1 by T1. So here your pressure is same, which is at 10 bar. So you can take that out. Your volume is also same, which is 1 meter cube. So R of nitrogen, that is also the same. So we can find by 8.314 divided by your molecular weight, which is 28. So at so we can take PV by R common. So into M1, so 1 by T1 minus 1 by T2. So we know temperature at state 1 which is 300 Kelvin and state 2 is 400 Kelvin. So substituting that, we can find out the mass which is going out, which is equal to 2.808 kg. So this is the amount of mass the nitrogen cylinder is losing by heating. So now again we will apply an energy balance across this cylinder. So when you apply an energy balance, this is equals to du Cv by dt, which is change in internal energy, equal to heat transfer which you are supplying minus there is no inlet to the cylinder, or there is only exit, so the exit enthalpy m minus m dot e He. So this is what you get. So and so if you expand uCv as mu, so you get m du by dt plus u dm by dt, and we write enthalpy He as u plus RT. So you see right hand side and left hand side, u dm by dt gets cancelled out. So ultimately what you will left out with is m into du by dt minus RT dm by dt. Dm by dt is nothing but me, the mass of nitrogen which is going out. So the other way of solving this is you can find out the change in internal energy directly using you can find out mass m1 and mass m2, and you can use Cv delta T, m1 Cv1 Cvt1 minus mcv T2. So you can use that also to find out. This is the other way of solving. And again for enthalpy at He, you can use mcp T. But I'm showing that's what we solved used in the previous problem. So this is the other way of solving. So we know we have simplified this into m du by dt minus RT dm by dt. So using ideal gas equation, you can write a mass as PV by RT. So we are differentiating mass with respect to temperature. So dm is PV by R into dt by minus T square. So QCV is PV by RT into CV dt by capital T is temperature, small t is time. So dt by dt plus dm by dt, which we have already found out, into RT. So substituting this gets simplified into PV by R into Cv plus R into 1 by T into dt by dt. So Cv plus R is nothing but Cp. So this whole expression will come down to PV Cp by R into dt by T. So now if you integrate this with respect to time, this will come out to be PV Cp by R. This unknown is variable is with respect to temperature. So integrating ln T2 by T1. So this is what you get for heat transfer expression. So we know pressure, we know volume, we know Cp, which is Cv plus R. And for nitrogen, it's given as 1.041 kilojoule per kg Kelvin. And we know temperature at 2, which is 400 Kelvin, and T1 is 300 Kelvin. So substituting that in the expression, we'll get your heat transfer is 1000 megawatt. Sorry, 1 megajoule, or 1000 kilojoule. 1009 kilojoule. Turned out we have wrote an energy balance equation. So du Cv by dt equals heat transfer minus the enthalpy of the stream which is going out. So then we expanded the enthalpy term, and also the uCv terms we wrote in terms of specific internal energy and mass. So we expanded that, and we found out a simplified expression for heat transfer, and then we applied ideal gas equation to find out mass, and we expressed the mass expression into terms of change in temperature with respect to time. So So we found out dm by dt into dt by dt. That's what we did. So substituting that, we found out few terms in terms of temperature. So and we integrated. We found out a simplified expression which is PVCP by R into ln T2 by T1. So, and we substituted all the values and we found out the heat transfer. Any doubts? I think I've finished all the problems which I've taken. If you have any doubts, you can ask.
No, sir, everything is okay, sir.
Today was all recap of all the problems in the previous weeks. So we have tried a different set of problems, but the process will all remain same. You have to apply in mass balance, you have to apply in energy balance, you will solve the most of the problems. If you have any questions, you can ask, or else I have finished what I have prepared for today. You can wind up. If you have any problem questions, you can ask. Yes.
So,
Yeah.
while solving the problems given in the assignment,
Okay.
the problems little bit difficult. No?
Okay.
The problem actually, while answering the assignment questions,
Okay.
the problems are little bit difficult.
Uh,
Actually, the problems are practically oriented based on that. No?
yes.
So, little bit tough.
But that is how the professor has designed the course. I don't have any this thing on assignments.
Okay, I will bring this to your knowledge. That's all. And one more thing, no, so when will you know this no, marks progress no, for that last previous assignment six, no, assignment number six?
I think they will frequently update it on the portal. You can see that.
Okay, okay, sir. Okay, sir. Thank you.
Thank you. If you have any questions related to the concept or this thing, you can ask, or else you can end the session. Okay, then if you don't have any questions, thank you for attending. I'll also come up with similar problems for next week. We'll see air standard cycles and Rankine cycle, similar problems on that. Uh, so today was a recap of all the first law and second law related to problems. We'll mostly solve the next week. We'll solve regarding cycles. We'll see questions regarding that. Thank you for attending. Thank you.
Okay, sir. So we are leaving, sir.
Yeah. Thank you.
Okay, sir. Thanks a lot, sir.
Yeah.
And whatever the proportion that not yet able to continue, that I will check from the video. Okay, sir.
Yeah. I'll upload the video and the slides soon. You can check that.
Okay, sir. I used to see your video every day, and I also follow your class. No problem, sir. No, thank you, sir.
Thank you. Thank you.
Very good class, sir. Thank you, sir.